Hello students, in this video we'll see an example of changing a double integral into polar coordinates. Let's consider the region described geometrically as follows. So rather than writing out the region in Cartesian coordinates, which would be a little bit of a mess, I'll define the region by a picture. So here's our region. We're going to look in the first and second quadrants. Here's the x-axis, here's the y-axis. What I'm going to do is I'm going to draw a circle of radius 2, a semicircle of radius 2, and then a semicircle of radius 1. So I have those two arcs over there, so those are circles. In other words, this curve over here is x squared plus y squared is equal to 4. And this curve over here is equal to x squared plus y squared is equal to 1. And we're restricting to x and y greater than or equal to 0 in this problem. So x and y in this problem are going to be greater than or equal to 0. More than that, what I'm going to do is I'm going to draw this line y equals x. That's the line y equals x. And I'm going to draw this line over here, y equals negative x. That's y equals negative x. And I'm going to shade in this region between these two semicircles between y equals x and y equals negative x. And that's going to be our region over here. I'm going to call this region over here D. That is our region D. What I'd like to do is I'd like to find the double integral over this region D of, let's do it like this. Let's do tangent inverse of y over x times the square root of x squared plus y squared dx dy. Now this integral looks like a mess in Cartesian coordinates. I don't even have what the x and the y limits are doing. I'm just writing the integral over d. What I'd like to do is I'd like to change this region to polar coordinates. So remember, when we change to polar coordinates, a couple things happen. In polar coordinates, x becomes r cosine theta, y becomes r sine theta, r squared becomes x squared plus y squared, and theta becomes tangent inverse of y over x. Then these are how the x and y and r and theta look. I know that dx dy in polar coordinates turns into r dr d theta. So my differential element changes, and then my limits of integration change. Well, we can notice that there's a relationship between x and y and r and theta. In this region, x and y reside within the region D. So a point x and y is in my limits of integration, my bounds of integration, if and only if what? If and only if r and theta reside in this new region D tilde. And what is this new region D tilde? D tilde is a set of points r and theta such that what? Let's think about what's happening in this region. The line y equals x corresponds to what kind of an angle? That corresponds to an angle of 45 degrees or pi over 4 radians. Y equals negative x corresponds to an angle of 3 pi over 4. So in this region, my angular variable theta goes between pi over 4 and 3 pi over 4, whereas my radial variable r goes between 1 and 2. Circles of radius 1, circles of radius 2. So this region between two circles in polar coordinates, and between two line segments, two rays, in polar coordinates turns into a rectangular region, because this region over here is just an interval for theta and an interval for r. It's a rectangular region. Now we can turn our integral into polar coordinates. It becomes what? In polar coordinates, our problem becomes this. So my limits are going to change. My limits, our integral, is the integral. Theta goes between pi over 4 and 3 pi over 4. R goes between 1 and 2. And then let's change our functions. Well, this is tangent inverse of y over x. What we mean is we want this tangent inverse to represent also what? Just the angular variable theta. So really when I write this tangent inverse of y over x, I mean it to include all the values, all the correct reference angles, so that I'm able to get into the what? In the second quadrant as well. I didn't have to define this function piecewise. I just wanted to show you, illustrate that tangent inverse of y over x is meant to be the angular variable theta up to the correct reference angle of what quadrant you're in. So we're going to replace this tangent inverse of y over x with a theta. And then this x squared plus y squared, square rooted, is r. And then I replace dx dy with r dr d theta. And so now I have what? Now I have a function of theta times a function of r. This is really r squared. And so this is by rectangular separation, since I have a function of r times a function of theta. So by rectangular separation. And rectangular separation happens frequently in polar coordinates because we tend to write down problems in textbooks that are regions between sectors of circles. So we typically like to see problems where we change the polar coordinates, it turns into a rectangle. This will be the integral from pi over 4 to 3 pi over 4 of theta d theta times the integral from 1 to 2 of r squared dr. Now perform both these integrations. So I'll have a theta squared over 2. So theta squared over 2 from 3 pi over 4, from pi over 4 down to, 3 pi over 2. 3 pi over 4 to 4, pi over 4. And then what? Then we'll have a times the times what? Times we'll have a r cubed over 3, evaluated from 1 to 2. So now we just simplify this. When I do 3 pi over 4 squared, I get a 9 pi over 16. So that's going to be a 9 pi, and then I have a 16 over 2, so that's going to be a 32. Minus, when I plug in pi over 4, I'm going to get pi squared over 16. So I'm going to have a pi over 32. And then when I plug in 3 to this, I'll have a 8/3 minus 1/3. So I have an 8/3 minus 1/3. So if we simplify this, what do we get? We get an 8 over 32. Well, of course, 8 pi over 32 is going to be, 8 pi over 32 is 1/4, so this is pi over 4 for the first thing, and then times 7 over 3. So our final answer is 7 pi over 12. So by turning the problem into polar coordinates, we didn't have to deal with this messy integral over here, which would have involved a lot of sort of crazy substitutions. We can just simply change the problem into polar coordinates, and then it basically will turn into a rectangular separation problem where the integration is very easy to compute. Thank you very much.